In part one of this set of notes, we talked about the form of the relationship in a scatter plot and the direction of the relationship. Now we're going to look at the strength of the relationship. So at the beginning of the next page, you'll see that the strength of a scatter plot tells us how close the points are to some sort of line or pattern that could be drawn. If the points are all very close to a line or pattern, we refer to that as a strong relationship. We're essentially saying there's a very clear pattern that's happening here. There's something that we could describe to someone where if we knew one of the variables, it would be very helpful in having us predict the other variable, for example. On the other hand, you may see a line or pattern on your graph, but the points may all be fairly scattered around it, and so we might refer to that as sort of a weak relationship. And this all is on a spectrum, and so you could have, say, a moderate relationship as well. So just a few examples of this. Here's 3 graphs. For each one, I've drawn the points, or draw the line that I think sort of describes the pattern that I'm seeing here. And what I want you to look at is, in which case are the points closest to the line that's drawn, in which case are they furthest from the line that's drawn, and in which case are they maybe sort of somewhere in between. And if you do that, you might notice that on the right, these points are all pretty close to the line. The line I drew maybe isn't the best one, but all of the points are pretty close to it. So it looks like there's a strong relationship between whatever my x and my y variables are here. On the other hand, over here on the left, there is a pattern that's we're able to see. You can tell that as x goes up, y also tends to go up, but the points are pretty scattered above and below the line. Like take, for example, right here, when x is a little bit above 10, I've got one y value way down here, close to 4. I've got one y value way up here around 6.5. There's a lot of variability around that line. And the graph in the middle is sort of somewhere in between. So we might say that this one is sort of a weak relationship, this one's kind of moderate, and this one is pretty strong. And I said that this could be a relationship about a line or pattern, so not necessarily a straight line. We could talk about the strength of a nonlinear relationship, for example. So down here you can see that these points do not look like a straight line. If I drew a straight line, it wouldn't really match up with what I'm seeing very well. But there is a very strong relationship there. I can draw a pattern that fits these lines very closely. On the other hand, something over here, this is pretty weak, kind of like we saw over on the left side up above. And again, this is not a linear relationship in the middle, but there's a moderate relationship there. The points are spread around the pattern, but it's a lot clearer of a pattern than this one maybe. All right. So again, we can talk about the form, we can talk about the direction, and we can talk about the strength. So if you revisit the Challenger scatter plot, we've got it here. If we look at the form, it's a little hard to tell. When I've done this in the past, some people will say linear. They'll say you can kind of draw a line like this that looks like it fits the pattern fairly well. Some people might say nonlinear, like they think that there's kind of this curved pattern that they would see showing up. I think both of those are reasonable. We don't have a ton of data here, and so it's hard to really get a good sense of the pattern. So you could probably go either way. In terms of the direction, though, both of those look like a negative direction. So whether it's curved or straight line, it looks like the direction is negative. As you get lower for temperature, it looks like you're getting higher for index. As you get higher for temperature, it looks like you're getting lower for index. And then the strength is another one that's a little hard on this graph because we don't have too many points. So people tend to want to say sort of weak or moderate. We'll revisit this. I might describe it as moderate, but because you can tell that it is a little bit difficult to classify it into one of those categories, our next step will be to talk about how we can quantify the strength so that we don't have to sort of guess at which one of these it might be. All right, so I've got this in the notes here. So we've done things like this throughout the semester. we sort of generally talked about like how spread out a data set was, and then we realized that it would be useful to have something like the standard deviation to give us a number describing it. And you could kind of talk about where the middle of a data set is, but then it's useful to have something like the mean or the median to describe it in a number. So that's what we're going to do here. The correlation coefficient, we write it as R. It's also known as the sample correlation. This helps us describe the strength and direction of a linear relationship. And I've got the steps for how we could calculate it. This is the formula here. We are not going to calculate this by hand. I wanted to show you the steps real quick so you know where this number is coming from. Essentially what we're doing is we're looking at how our x value compares to the mean, how our y value compares to the mean. We're putting that together, we're adding it up for all of our values, and it's giving us one number. All right. So this number, like I said, tells us the strength and the direction for a linear relationship. So the first thing that I want to emphasize, it really only makes sense to talk about this sample correlation or the correlation coefficient if your relationship is linear. If it's not, this number doesn't really tell us a whole lot. The other thing I'm going to point out here is that there's no units. So I might say the correlation is 0.5. No units with that. I don't have to say inches or meters or pounds or whatever it might be. It's already sort of scaled from there. So one thing that I would like you to do if you're going through this for the first time is visit this website here, play around with it, and see if you can answer the questions below that have some blanks and things like that. If you visit the link, it'll give you this sort of blank graph, and you can kind of click on it to draw points and things like that. And so I'll illustrate a couple of these for you. So the first one asks, when all data lie on a straight line with a positive slope, what is the correlation? And so I could try to do that. I'm probably not going to be able to get my line perfectly straight, but that's got a positive slope. It's as close to straight as I can make it. And you can see that my correlation is really, really close to 1. So it seems like maybe if those points really were perfectly on a straight line with a positive slope, I might get a correlation of 1. And that is in fact true. If I clear the data and I want to know, well, what if I have a perfectly straight line with a negative slope? And again, I can do my best. I'm not going to get it exact, but here's a negative slope. You can see that I get a correlation really, really close to -1. And so again, we might suspect, and you would be correct, that if all of your data lie on a perfectly straight line with a negative slope, you get a correlation of -1. So what this means is that the correlation coefficient, or the sample correlation, can take on any values between -1 and +1. Those are the two extremes. All right? So we can see how the positive or negative version of our correlation relates to the direction of the graph. When we have a positive slope, we called that a positive direction, and our correlation will be a positive number. When we had a negative slope, we called that a negative direction, and our correlation is going to be a negative number. So right away, just by calculating this number, it tells us the direction of our linear relationship. You might also have noticed that perfectly straight lines were with slopes of 1 or correlations of 1 or -1. What that means is that if we have a really, really strong relationship, our absolute value of our correlation is close to 1. So it's either close to +1 or -1. The flip side of that is that if our correlation is close to 0, that's describing a really weak relationship. So up here, we said that the correlation coefficient can describe the strength. Is it close to positive or -1, or is it close to 0? And it can describe the direction. Is it a positive number or a negative number? So we don't have to try to guess at this and say, it's kind of moderate, maybe weak. We can use this number to help us out. couple other things that I want to point out about the correlation. It is unaffected by which variable is x and which is y. So you could try to look at that on the graph where you draw points, but it actually doesn't matter which is which for calculating the number. It also doesn't matter if you change the units of measurement. So if I'm measuring someone's weight in pounds and I'm measuring their weight in kilograms, both of those will have the same correlation with the person's height, for example. There's an activity that you'll do where you'll look at this in a little more detail. I also wanted to talk about correlations of 0. So people tend to think of this graph on the left, where you just sort of have a blob of points with no real detectable pattern. And you're right that that will have a correlation of right around 0. But that's not the only thing that has a correlation of around 0. I might also have a graph like this, where part of it has a positive direction and part of it has a negative direction, and those things sort of cancel out and tell me that the correlation is around 0. This is why we said it's really important that this can only describe a linear relationship between two variables. Because something like this is a very clear pattern. There is a strong relationship between these two things. It just so happens that that relationship is not linear, and so the correlation coefficient will be close to 0 and make it seem like there's not much of a relationship. You could also have sort of a flat line here. This would be a case where pretty much everybody has the same y value, and so x doesn't really help us understand y because there's not really a relationship. All of the y values are basically the same. Couple other things. The correlation coefficient is very affected by outliers. So I'll give you an example that's right here. I did this in the link that I showed you. This set of points has a sample correlation of 0.998, very, very close to 1. After I made that graph, I added one more point to the graph and I put it down here. All of a sudden, my correlation went from close to 1 to around 0.4, so closer to 0 than it is to 1. That is a little bit of a problem. There's not a huge difference between these two graphs, but our sample correlation is telling us very different things. So you really want to be careful about using this number when you have outliers present. So if there is an outlier in your data, maybe this correlation isn't the best way of describing it. And then one last thing that I want to discuss about correlations. You've probably heard the expression, correlation does not imply causation. What we mean by this is that just because two things are correlated does not mean one of those causes a change in the other. So one example is if you had data on the amount of ice cream that was sold in a city and the number of sunburns, there would likely be a positive correlation between those. That doesn't mean that the city should petition for ice cream to stop being sold because people are getting sunburnt because of it. Instead, both of these things just happen in hot weather. And so there is a relationship between them. They both tend to be high at the same time of the year. They both tend to be low at the same time of the year. But it doesn't mean that either one is affecting the other. All right. So when we say correlation does not imply causation, we're talking about things like this. That doesn't mean that something can have, some effect. So for example, height and weight. Those things are correlated, and there probably is some sort of causation. As you get taller, there's more of you, and so your weight will go up a little bit. Now, height is not the only thing that causes changes in weight, but it is one thing. So in that case, there's a correlation and a causation. In the ice cream and the sunburn example, there is only a correlation, not a causation. All right? So in the next part of the video, we will talk about how to have SAS calculate these correlations for us and how we can use them in hypothesis tests as well.